want to talk about something that is pretty exciting in terms of where things are going. So I want to talk about multi-threading versus asynchronous programming and where this makes a big difference from the point of view of architecture. But I want to get down to the code level, and I want to be hands-on talking about what this means in developing applications. I was fascinated by multi-threading, parallel processing. I spent a number of years programming and focusing on parallel computing. But over the past few years, I've realized that while parallel computing is still interesting and useful, we need to really shift our focus on more asynchronous programming. So that's what I want to talk about here today, is why that is really important. Then we will talk a little bit about how we can actually achieve it and between different versions of Java as well. So let's talk about where the world has been and what we have been doing and how we have been creating software as well. So when it comes to writing applications, if you've ever done any programming, and I'm sure that I'm in a room full of people who write code all the time, we all have written code in sequential applications. You start by learning programming by writing sequential code, but you also write a lot of sequential code. But I would ask the question, how do you know you're writing code that is sequential? I'll tell you there's a very easy way to know that. If you're writing sequential code, if you go to work, people will actually smile at each other. That's how you know you're writing sequential code, right? They are friendly to each other, they're nice to each other. You go to lunch together as a team. That's how you know you're writing sequential code, right? You write the code, you understand it, it works. Then you know it's a sequential code. And you've been using this sequential code for a while, and then you realize that the code has a few issues. Like what? They tell you the code is not very responsive. You have made a request to go search for something, and while the code is searching for the data, you want to interrupt it, and your application is not responding. Or when the application is doing some work, you want to start another search. They're telling you it's not responding. Or the performance is not adequate. But a lot of times it's responsiveness. So you're sitting with your team and they're talking about it, and they ask you the question, how can we make the code more responsive? And somebody in your team says, I've got an idea. And you say, what is it? And they say, let's use multi-threading. That moment, when you heard those words, is the last time there was joy at work. Because now everybody is grumpy. Because the code that you could once understand has turned into a monster. You can't even recognize it. Every few weeks, you go into the repository and roll back the changes to a few weeks ago so you can just look at how it was and how your life was before this monster came about, isn't it? And there's locks everywhere and you're synchronizing everywhere. You can't understand the code, but it doesn't work. So you haven't gone home. At deep late in the night, you're debugging the code and you're losing your patience. And in the middle of debugging, you decide you want to apply for a different job. You know what that means, right? That's called concurrency. Because you said, I've had enough of it. I can't handle this anymore. I'm going to go look for another job. So that's how you know how the code has turned into multi-threading. Now, I like programming a lot, but I also like philosophy. So here's my philosophy. And this is something I've come about learning over the years. And that is, to me, is in both in life and programming. We solve a set of problems only to realize now we have created a new set of problems. This is definitely true about life. Okay, there you go. That's concurrency right there, right? You write it once and it repeats so many times. I didn't mean that, sorry. So essentially, both in life and programming, we create solve one set of problems only to realize we have created a new set of problems. Well, if you want an example of that, you are in the right place. Because when Java was introduced back in time, this is 28, 29 years ago, What did they tell us? Hey, you can do multi-threading in Java from day one. So what did they do? They introduced the thread API. And some of you may be old enough that you use that library. Others have heard about it. And you can create threads in Java. You could create threads. You can say new thread. Nobody does that anytime, in recent times. But then we realized we just don't want threads. We want pool of threads. So why? Because you don't want a problem. You want a pool of problems. So you create a thread pool. And then we realized, yeah, that's not a really nice way to deal with it. So then in Java 5, what was the aha in Java 5 from the concurrency point of view? That was your executor services, isn't it? So you could create executor services, and all of a sudden, executor services is managing a pool of threads, potentially, but you just schedule your task on executor services, it runs your task, and then you can manage it, you can shut it down when you don't need it, you can await for termination. Rather than having to deal with threads directly, we deal with executor services. That becomes your scheduler. So that was like, whoa, that's amazing. And that was Java 5. And then, of course, we solved a problem. What was that? You're not going to deal with threads individually, you deal with executor services. But then, after Java 5 came out, a couple of years went by, and people started noticing something really weird. I actually ran into this on a project, and it's very frustrating because when you learn some problem the first time, you're just discovering, right? This is just blowing up on your face. And what I found out was that, let's take a silly scenario, a little example to understand what this means. Imagine, let's take a very trivial example so it's easier to understand this. Imagine I create an executor service, a pool with 2 threads in it, as a very simplistic example. I schedule one task on it. The task is executing on this thread in the pool, finishes the job, end of story, no problem. Now let's take a task which is a little bit bigger. So you schedule the task, it runs on this thread. That task is broken into 2 child tasks. So now you have 2 children tasks waiting to run. And now you schedule the first task on the second thread. It finishes. The second task gets scheduled on the second thread. It finishes. The main task now takes the 2 results, finish the work, end of story. No problem. Now let's throw a little bit of a bigger problem into this now. So now you schedule a task. The task is running on thread 1, and the task now split into 2 tasks. So the 2 tasks are waiting for their turn. You schedule one task on the second thread. Because the problem is big enough, it breaks into 2 children tasks. Now in the queue, there are 3 tasks waiting. You are with me, right? So because we broke the first task into 2, each of the tasks now broke into 2 more tasks. So we have 3 waiting. And you ask these tasks, what are you waiting for? We want to run, so we're waiting for a chance to run in the queue. And you ask these 2 tasks what they're doing. They're saying, we're waiting for those tasks to complete. As it turns out, this is called a pool-induced deadlock, which is very frustrating when this happens. So yes, you create a pool, but when the problem size is big enough, you run into a pool-induced deadlock. We solved one set of problems only to create a new set of problems. And they said, oops, that's not going to work really well. And now you know why they introduced the fork join pool. Fork join pool says, hey, we'll do work stealing. So if a task is split into children tasks, what is this task doing holding on to the thread? So when it splits into children tasks, it can let go of the thread in the pool so the children task can run. When the children tasks are finished, we can reassign the thread to run the parent task, and then it can finish up. So we are avoiding the pool-induced deadlock by introducing the fork join pool. So you can see the evolution of the threading API in Java through Java 1 and Java 5 and Java 7. And then, of course, you may say, we're done, right? As it turns out, no, we're not done yet. So we seem to be going a little further. But let's talk about the life and the journey, if you will. So in the past, I think we all can agree on it, right? In the past, the structure of imperative style, so we can say imperative style, parallel code is or you can even say from the past, not just in the past, is very different from the structure of sequential imperative style, you could say imperative style sequential code. So essentially, that's basically what we've been noticing over the years. So from the past, the structure of imperative style parallel code is very different from the structure of imperative style sequential code. If I showed you a parallel code and I showed you a sequential code and say, do you realize they are doing the same thing? You're like, no, that's so different from each other. You took what was so nice and easy to understand, and now you tore it apart with all these synchronization primitives, and the code is a monster that you cannot even recognize anymore, isn't it? So that's the world we lived in terms of how these things look like. Now, having said that, let's kind of step back a little bit and think about this concept for a minute, if you don't mind. We often talk about parallel and concurrent. This is confusing to a lot of people. What does it mean to be parallel? What does it mean to be concurrent? How are they different? Well, I just demonstrated that just a second ago, if you noticed it. I just showed you the difference between parallel and concurrent. So I'm walking on the stage, but while I'm walking on the stage, I can speak at the same exact time. That is in parallel. I don't have to stop to say a few words and then be quiet and take a few steps. So I can speak and walk in parallel. It would be rather very impolite and maybe even not good for the health to speak and drink at the same time. I won't do that in front of you. That's very uncivil to be speaking and drinking at the same time. It turns out I can speak and drink only concurrently. I shouldn't try to do that in parallel. Why so? So if you take a timeline, if you will, on the timeline, you can think about it as, if here is a timeline, in this timeline, I can, at any given time, I can talk, and at the same time, while I'm talking, I can also be walking as well, so that is parallel. I don't have to stop talking to walk. I don't have to stop walking to talk. I can do them in parallel. On the other hand, at any given timeline, if you will, I can either talk or drink, or talk or drink, but I cannot do them at the very same time. So in the hour, I'm going to say several words. In the hour, I might empty maybe half of this bottle of water. I don't have to stop talking or keep talking until the end and say, hold on, folks, and then finish gulping this water. I don't have to do that. While I'm giving this talk, I can say some words. I can pause for a second, drink a few sips of water. I can keep talking again, pause again, and drink some water. So in an hour, I would have said so many words. I would have emptied so much of water, but I'm doing it in concurrent, not sequentially. But I'm not doing it in parallel. As you can see, the mouth can only either say a word or take a sip of water, not do both safely and politely. So that's very concurrent. So that kind of gives us an idea of what does it mean to be parallel and what is it to be concurrent. In a given time, both parallel and concurrent tasks make progress. But parallel tasks can run at the exact same instance, whereas concurrent tasks really are sharing and then switching back and forth in executing those tasks. We've been doing concurrent and parallel for a long time, but now of late we are thinking more about asynchronous programming. So what does it really mean to be asynchronous? So asynchronous programming is taking more importance. And so what does it mean to be asynchronous? It means non-blocking calls. Now, what in the world does non-blocking call really mean? So I'm going to go make a request to a database and say, hey, database, get me this data. Or I'm going to make a request to a remote web service and say, hey, web service, give me this customer's account information. Or I'm going to go to this microservice and make a request. So when you make a request for data, so if you ask for data, you have to wait for the result. So all tasks are always blocking unless they do not care for the data. Those are called the fire and forget models. You fire a request, but you don't need any response. You keep walking away. It's like you give somebody money and say, hey, here's the money for the item I purchased. By the way, keep the change. I don't need the change. You can walk away. You're not really interested in anything back from them. So that's a fire and forget. But if you're performing any task where you need the data, you cannot say, I would like to have a cup of coffee, please, and then you're gone. And they're like, where did the dude go after asking for a coffee, right? That wouldn't make any sense. So every task that needs a response of a data has to be blocking. So what in the world does non-blocking mean? And the problem here is when a task blocks, the thread, let me say sadly, blocks with it. So think about that for a minute. So in other words, when we say blocking versus non-blocking, what are we talking about? We are talking about the thread of execution. This is what we are really concerned about because of execution, right? Because tasks are always blocking. The question really is, what does the thread do? Now let's think about this with a few different examples. How many of you are parents in this room? Wow, that's quite a number. Parents of toddlers, little kids. Well, quite a few of you, right? I'm going to take some examples from the people in the front row here. You know how tiring it is to have toddlers, right? They got energy. You're like, where is this battery that keeps running them? They're like, keep running. You're like, oh my gosh, my head is spinning, right? And eventually the toddler, not in those words, but eventually the toddler says, I'm going to take a nap. And you're like, my goodness, thank you. And as a parent, what do you say? Your kid says, I'm sleepy. You said, that's a great idea. Let's sleep together. Do you do that? No, you shouldn't. Because no work ever gets done. So as a responsible parent, we got some talking to do. As a responsible parent, what do? You say, here child, take a nap. And the minute the child takes a nap, what do? You're off doing your dishes. You're off doing other work until the child wakes up and you're back right there and the child doesn't even know. And the child is like, where were you? I was right here, right? The little sweet lies we keep telling. That's what you do really, right? Okay, just to be sure. Now, on the other hand, if you sleep along with the child, then you are like the thread in Java. Because the task says, I want to sleep. The thread says, great idea. Let's sleep together. So you say, wait, I created a thread. The thread is calling the task. The task is taking some time. And the thread says, don't worry about it. I'll be here for you. And you're like, wait, but the application is not responsive. What should we do? Ta-da! Create more threads. Why are we creating more threads? Because the threads suck, so create more of them. How does that logic sound to you? It doesn't do a good job, so create more of it. That's what we've been doing. And what does this affect? The S word. When I talk about something, we always hear this S word. When I refer to it, nobody wants to say it. Scalability. Thank you. I was getting worried. It affects scalability, right? You're like, oh, that's what we're talking about, scalability, right? Why is it affecting scalability? Because if your threads are busy, how do you do more things? We got to create more threads. And how many threads can you create on a machine? It depends on two things. It depends on the number of cores and depends on the amount of memory. So now your application requires a lot of processing. You want to handle 20,000 requests. And you're like, whoops, I cannot create 20,000 threads on this machine. What do? We got to scale. Oh, here's an idea. Let's create a cluster of machines. And the people running the cloud servers, the Amazons and the Googles and the Azures, and keep going. And they are like, it's okay, keep going. I like where you're going with this. Come on. And their bosses are like, how many servers are you using? Right? You need more accounts, by the way. Let's talk about it. In the meantime, we are screwing the environment because we are having clusters of machine. Why? Because our threads suck. Because they get blocked when the thread task block. So when the little toddler sleeps, what do you think? We don't want to sleep with them, right? So imagine you go into a restaurant and there are amazing waiters in the restaurant and you are sitting there and the waiter comes to you and says, hey, excuse me, what would you like to drink? And you tell the waiter, what do you have for drinking? And the waiter gives you a list of things you can order to drink. And you're like, I'm not sure what I'm in the mood to drink. And then people sometimes ask this question. I never understand these people. They ask you, what's your favorite? How does it matter what's the favorite of a random waiter? But people always ask that. This fascinates me. What's your favorite? I'm like, how does it matter what my favorite is? It's what you want to drink. But anyway, what's your favorite? And they tell you what their favorite is. Like, interesting. Do you say, I'm still not able to make my mind? What does the worst waiter in the world say? The worst waiter in the world says, let me grab a chair. Sits next to you. Let's talk about it. How's your day going? This is the irony. A good waiter should never wait. What irony? If you're a waiter, what do? You don't wait. You tell the customer, you know what? Why don't you think about this? I'll be right back. And you bolt away and you go serve other tables. Because if you don't, the people at the other table are starving and thirsty and complain. And they never come back to your restaurant. They say, that's a very bad restaurant. The waiters just abandoned us. So a good waiter keeps shifting between the tables. You're having your meal. Some waiter who's walking by with the jar says, hey, your water is low. And they pour water. You don't say, stop. You are not the waiter for my table. How dare you pour water for me? That's a way to get kicked out of the restaurant, right? It shouldn't matter to you who is pouring water. You're thirsty and somebody's serving water. So what if threads become like waiters in restaurants, where they don't block and wait? When your task is blocking, your thread is blocking, and that's no good. What if your task is blocking and your thread says, hey, you wait there. You can block and wait for your I/O. I'm going to go work with other requests right now. And when you're done with your request, when you need a thread to run, we'll give you a thread to run right away. So that's basically what asynchronous programming is all about. So the idea behind this is when a task blocks, we do not want the underlying thread to block. So now we know what non-blocking APIs are. So a non-blocking is about the thread of execution. And why? It directly impacts your scalability. And that's why this is an architectural concern. Because in an architecture, if you want to provide scale, you don't want to block and wait. Because if you block and wait, meaning the thread is waiting, there's only so many requests you can serve. And in order for you to serve more requests, you have to go to clusters of machines. That complicates your architecture even more, because now you have to deal with the distribution. And you're having a bigger architectural impact because the threads have been designed to be blocking. So that is the whole idea of going towards non-blocking. So we want to really think about asynchronous programming because our business and architectural needs require a very high degree of scale. You say, hey, Venkat, we don't have any need for scalability. By the way, that's perfectly fine. Don't assume every application needs scaling. It doesn't. There are applications where scaling is important. There are applications where performance is important. There is applications where neither one of them is important. There are other concerns. If you try to force into an architecture what is not important to the business, you fail big. Because when you provide something, that often makes it hard to provide something else. If you provide what is not needed, it deprives you of providing what is actually needed. So it's not about my feeling or your feeling. You can like scale. That's like saying you like ice cream. That doesn't mean anything. Because the question is, what does the application need from the architecture point of view based on the business requirements? But if your business requires scalability, then we want to rethink about being asynchronous. Programming asynchronous is also difficult. Well, can be. So if you opt for it when you don't need it, you increase the complexity for no benefit. And this is why we got to be very careful in the choices we make. So the question is, all right, we are convinced we definitely need scalability in that application. What are the ways to provide that kind of scalability? It turns out, in the case of Java, there are two ways to achieve this. One is called completable future. But before going into completable future, let's talk about this for a minute. Going back to what I said earlier about in the past, right, from the past. So let's go back to this and add it. So starting Java 8, the structure of functional style parallel code is the same as the structure of functional style sequential code, thanks to, what should we send the thanks to? No, it's not Lambda. Starting Java 8, what was that? Thank you. Thanks to streams. The streams did this, isn't it? So what can you do with the streams? I can do this, isn't it? For example, if you want to think about it for a second, I can do the following. I can say, just as an example, let's say I have a little example here where I say names is equal to some names. Let's start with that. So given these names, I want to say here's a list of names, and I can say something like this, isn't it? Names.stream.filter, given a name.length is equal to, let's say, 4. .map, let's take a string and 2 uppercase. We can convert it. And then for each, system.out, and we can do a print line, and we can print it. That's a sequential code, isn't it? So it gives you the Dory, Gil, and Nemo that is sequential. But you say, no, I want to run this in parallel. So what do? You take that exact code, you do .parallel, and now you can run that in parallel rather than sequential. So you remove that, it's sequential. You add that one line, it's parallel. So the structure of sequential and parallel code is exactly the same, isn't it? So unlike the past, if I show you a parallel code, you say, my gosh, I can't even recognize this from the sequential code that we once had. Whereas here, it's exactly the same structure. And that's got a huge amount of benefit. You can write the code, you can reason with it. If you don't need to be parallel, don't bother doing it. If you need it, if it's correct, you can make it parallel. What happens if the cost of doing something is cheap versus the cost of doing something is a lot? Think about it from the architecture point of view. If I tell you, The cost of doing it is cheap, versus the cost of doing this is expensive. How does it affect what you do? If the cost is cheap, you will postpone doing it. I don't need to worry about parallel. Oh my gosh, what if I need to make it parallel later on? Pfft, don't worry about it. You just toss this in and it's parallel. Ooh, I don't have to worry about it. Instead, you're an architect and somebody says, oh my gosh, this has got to be parallel. You're like, are you kidding me? That is 7 months of code change. You're like, my job is in line now. Because what if I tell the business, now that we realized it requires 7 months of change, they're going to fire me. So what do you say? Let's think hard right now. If it's got to be parallel, we should start doing it now. Why? Because the cost of change is very high. Your architectural change, the cost of change impacts your architectural decisions. So with parallel, in limited sense, this gave us relief because I can postpone it. And when you postpone it, what's the benefit? We all talk about this every day, isn't it? This is called last responsible moment. Last responsible moment is great because I can postpone the decision until I can no longer postpone it. But when you postpone decisions, what happens? You learn more about it because you can make your decision more informed. If you're ruled by the fear, you make decisions early. And when you make decisions early, you make decisions with fewer details on your hand. The chances of it being wrong is higher. And that's the trade-off you're going to, feel here. This eliminates that cost in the long run for you. That's a benefit. So, but that's great. But that's parallel. That's what you said. What about asynchronous code? What are we going to do for it? So let's take an example. Let's say public static. Let's say string fetch. I'm going to say here is a path I'm going to send to this function. And in this path, what am I going to do? I'm going to say return, let's say files dot read string path dot off path. So let's return the string from there. And because it's a checked exception, for now I will say catch exception, and I will simply say throw new runtime exception, and we'll wrap that into it. So I'm going to go ahead and bring in java.nio.file so we can bring that in. So we just wrote that little function, that's all we did. But I want to do this non-blocking. When I call that function, what's going to happen? It says, wait, you wait here until I read the file. And what is your thread doing? Right? I'm waiting for the file to be read. What are you doing waiting? Oh, let it come back. I will work with it, right? So your thread is underutilized, waiting for the I/O to be performed. This could be I/O, reading a file. It could be logging. It could be going to a remote web service. It could be waiting on a socket communication. It could be talking to a microservice. It could be just about anything that performs I/O, isn't it? It's going to be waiting for it. So what do you do in this particular case? I wanted this to be non-blocking. How do we do that? java.util.concurrent.star, and I'm going to say a public static completable future, and I'm going to say string, and we'll call it fetch async. This fetch async says, give me a string, which is the path, and let's see what we can do with it. So what does this say? Return completable future dot supply async. And it says, go ahead and call the fetch function and send the path to it and return a completable future. That's all we did, right? So we are returning a completable future. So now what are we going to do? The reason is we don't know what we want to do with the file. You may want to take the content, maybe print it out. You may want to take the content, get some data out of it. It could be any operations you want to perform. We don't know that. So what do we want to do in here? So we say, all right, we got the fetch async. So I'm going to keep this really simple. I'm just going to say sample.java. The file itself, we're going to ask it to read it. Then what do you say? Then apply. I've gotten a data. So what do I want to do? I got the length of the file. So I say, given the text from the file, return text.length. I want to know what the size of this is, right? You're asking for that information. Oh, thanks, you gave me the size. Then accept. And what am I going to do to accept? I want a system.out, and I want to print it. So print line. So when you do this, it's going to print it. Notice it didn't print anything expected. Why? Anyone want to guess? Because it is non-blocking, asynchronous. It didn't wait. The main didn't wait. The main said, here you go, I'm off. You're like, oh, where's the result? Again, I'm not suggesting you do this, but I just want to demonstrate it. .join, you're telling the main, just can you wait for that to finish? And that's the result you got from there because you joined on it. So that is asynchronous, right? It's non-blocking. It fired, and of course, the sequence of thread that's executing it says, I am going to now go get the data and then call the then apply, get the length, and then I'm printing it. So far, so good. If we stop this talk right now and say, thank you for coming, folks, you can leave. You're going to go home saying, oh my gosh, completable future is awesome. So if you want completable future to be awesome, I'll give you a pause, leave the room right now. But life is not that simple, isn't it? What's going to happen? So let's pause for a minute here before we get to the bad news. Let's go back here to this. And now, starting Java 8, the structure of functional style, asynchronous code is the same as the structure of functional style, synchronous code. Notice we're not talking about sequential, we're talking about synchronous. We're not talking about parallel, we are talking about asynchronous. Thanks to, what is that? Completable future, right? But what happens in reality? In reality, we make mistakes. Whoops! I did not type sample.java. I made a typo. Anyone here makes typos? All the time, right? My wife tells me, I type extremely fast. And then she pauses for a second. She says, you type extremely fast. Backspaces. That's what wives are for, right? They remind you, put you in place. She says, you type really fast backspaces. He's like, yeah, I can't type. I can be typing backspaces really quickly. You make a mistake. So what's going to happen? It's going to blow up with an exception, right? When it blows up with an exception, what do? Well, the problem with completable future is, the way this works is as follows. If all is well, go to the next then. If there is a failure, go to the next. Oh, we'll come to that in a minute. By the way, the people who wrote this API have a very interesting sense of humor. Really, if you think about it. If everything is good, you go to the next then. If something fails, you go to the next catch, right? Because what do you do when there's an exception? You catch it. But they thought we shouldn't call it catch. They decided to give it a very fantastic name. They said exceptionally. What does exceptionally mean? Something really failed and you're trying to deal with it. But exceptionally is a weird name, isn't it? But there's a reason for this. Because now you know what exceptionally means. So when your boss comes to you and says, how are things going? You say exceptionally. But you know what that means. Your colleagues know what that means. The boss just doesn't know it. So you want to catch an exception. What do? You write go to the next exceptionally. So I'm going to go back here and say public static void handle exception throwable. And what am I going to do with this throwable? Again, this is just one example. There are other things you can do. I'm going to type error all in uppercase like so, plus throwable. I'm going to print it right there and return null. I don't have anything to return right now. Notice this is an uppercase void, not lowercase void. So I come down here and say dot exceptionally. And you got an error and you output the error. So that's your exceptionally. So I go back to this code and say sample, and I run the code again. What does it do at this particular point is the question, right? What is that going to do? So we have this then exceptionally. I take an error. I'm going to print that error. Pardon me, I'm sleeping at the wheel, as you can see. Handle error, exception. That's why I wrote it. So I run the code right now. It got you the result. But I go back to this file and I change that. And I run the code. What does it do? It says error. And then it tells you that a sample without the A is not a valid file. Okay, so far? That is asynchronous. But imagine you have a piece of code where this is going to be then apply, and you have more of these then apply in the code right here. And you have more of the then apply. And something may go wrong here. Let's take that for a second. So what are you going to do to handle that error? You may write an exceptionally right there to deal with it. And the exceptionally may handle the error. You may go to the next level. If not, it's going to keep going. Now, when you look at this code, if I tell you in English that if there is an error, if there is everything going well, you go to the next then. If something goes wrong, you go to the next exceptionally. What do you say? You say, wow, that's a very nice idea, isn't it? And then I show you the code for it. And you look at this code, how do you feel? Do you feel like, yeah, that's awesome code? Or do you say, for heaven's sake, what in the world is this code doing? What's your feeling? First or the second? The second, right? You look at this code and say, what's happening here? And they say, let's talk about the path the code is going to take. It can come here and go that way, come here. By the way, if a code does all of that, what do we call that? Spaghetti code. And then they tell you, no, but it's functional style code. My argument is, it's dysfunctional style code. So here is where we need to have the ability to discern between. So there's the saying, right? There's a point of diminishing return. There are practices, you don't use them, you don't get the benefit. You start using the practices, you gain the benefit. And at some point, the more you use it, you lose it. So you need to understand where the tipping point is, the point of diminishing return. And in this case, don't get me wrong, I'm a huge fan of functional programming. But functional programming is awesome when your functions are pure. They do not have side effects. If your code has to deal with side effects or exceptions, functional programming is not ideal. Look at the code. It's no longer that cute little easy to follow code. It has turned into a spaghetti code. It becomes unmaintainable. And the more logic you have to process and more exceptions you have to deal with, that becomes incredibly hard, isn't it? So if you choose to use completable future, it's going to get really hard. Raise your hand if you've used completable futures. Or keep that hand up for a minute. Keep your hand up. Keep it up if you have found it to be increasingly easy to use when you are dealing with exceptions. There's not a single hand up, I think. And one person kind of slowly put the hand down. That's because, not because he found it easy to use, because the pain was just going through his body at the time. Is that true? The person who did that here, yeah? You could have seen this. This was beautiful. He's like, right? So that's the pain you can feel, right? So we all collectively agree. There are two kinds of people in this room who have felt the pain and the others who didn't have to. So that's the problem with this approach. But that was the answer in Java 8. But did you notice the unfortunate situation here? If your code is imperative, your code turns into a monster with parallel. If your code is functional style, it looks beautiful when you use parallel. It looks beautiful when you use asynchronous, as long as you don't deal with exceptions. But guess what? Mathematical operations are pure functions. I/O operations are impure operations. What is the first thing you're going to deal with when it comes to I/O? Exceptions. So you try to fit that into this model of completable future, it becomes incredibly hard to work with it. But I hate to tell you the truth, but I like to tell the truth. And so I want you to remember this. Completable future, has no future. Because it doesn't fit well for what we want to do. So I think I answered the question already, right? Which one should you use? Hopefully not that one. Because those who raise the hand, if I tell you, we got to continue to use completable future, what do? You're like, I'm going to find another job. Because that's not really effective, right? So we still have the problem. We don't want threads to get stuck. How can we solve the problem? Thankfully, we got an answer in Java 21, which is virtual threads. So what are virtual threads? Virtual threads essentially are super lightweight threads. That's right. They're super lightweight threads. Remember what threads are? Threads are lightweight. So when they created virtual threads, they wanted to say they are lightweight, but that word lightweight is taken already. So they said it's super lightweight now. So I hope there's no super lightweight later on, right? But it's a super lightweight thread. So in Java now, there are two types of threads. You have the carrier threads and you have virtual threads. Carrier threads are the threads given by your operating system. Virtual threads are purely JVM created threads. So you have carrier threads from the operating system, virtual threads from the JVM. So when you create a task, a virtual thread is attached to it. The virtual thread is mounted on a carrier thread, a mounting, like the cowboy mounts on a horse, right? So you're given this thread, carrier thread, and it's running. And your virtual thread, your task says, stop, I'm going to make an I/O call. And at that time, your virtual thread unmounts from your carrier thread. So your virtual thread says, don't worry about it, I'm here. Your task is attached to the virtual thread, and your virtual thread unmounts from the carrier thread. And what does the carrier thread do? It says, I'm going to go attend to other requests in my system. And the virtual thread is blocked and waiting on your task. Your task says, I'm done with my I/O. Oh, let's grab a carrier thread and the virtual thread is mounted on that career thread, and it runs. What's the benefit? The benefit is you can have a lot of virtual threads. You need very few career threads. So your system now needs 20,000 tasks to run. How many machines do you need for it? Just one. You didn't need a cluster. Now, I'm not telling you by any stretch of imagination, you don't need a cloud. That's not my message. Cloud has many purposes. I'm a small business. If you ask me how many customers are using your product, I'm going to say, yeah, maybe a few hundreds, sometimes less. So if I tell you I need scalability, you're going to say, Venkat, you have a problem. You don't need scalability. If your systems cannot run 100 users, you got a problem. So I tell you that my systems are running on the cloud. Then, well, why? Not for scalability at all. It's for availability. Because if one of my system crashes, even though I don't have a lot of users, they're still important to me. And I want them to have the system available. So I got a couple of different servers running for availability, not for scalability. So there are several reasons you may use cloud, but scalability doesn't have to be one reason. So how is this going to look like moving forward? Let's take a look. So I'm going to go back to this code. We're going to keep this fetch function, but let's get rid of all the other things here, if you will. And I'm going to go back to this code, and I'm going to say, hey, I want to go ahead and make this call, but how am I going to make this call? And there are several options for it, but I'm going to just show you one option just to give you an understanding. So here I'm going to say, when you come in here, I'm going to output, let's say over here, a thread dot current thread. So I want to display the thread information for you right there as you enter. So I say enter, and then I will print out that information. Similarly, I'm going to take this value, a var result is equal to, return the result in the end. And when I finish return, before I return it, I'm going to say output, and I'm going to say after, and I'm going to say thread dot current thread. If you don't mind, we can display that, right? Current thread. So we display the thread in here and thread in there as well. And just to make this a little bit more interesting, if you don't mind, I'll say index. So we can kind of take a look at it as well. So I'm going to say index plus and enter. Similarly, I'm going to say index plus after. So then we're going to come in, display that, and move on. That's all we are doing. So I'm going to come in here and say max is equal to, let's take 5 for int I equal to 0, I less than max, and let's say I plus plus. Again, you wouldn't want to really create threads like this, but I just want to demonstrate in a simple way. So I'm going to say a thread is equal to new thread, and I'm going to say in here int index equal to I, and I will say this is going to be taking on the fetch, and I will send the index right there, comma, and the sample dot Java is the file I want to read. So then I say thread dot start, isn't it? Let's make our life a little easier. So I'll simply say dot start. So I'm starting the thread right there as soon as we enter it. Then I'm going to say over here, let's simply say, we'll just wait for a little while. So try thread dot, let's say, sleep for about 5 seconds, and catch exception, keep moving. So let's start with this little example here, right? So what does this do for us? That's the question I want to start with. So I want to see the output in a meaningful way here. So let's take a look at this really quickly from the command line, so we can see what it's going to do and how it's going to execute this particular call, so we can take a look at it. So I'm going to simply say run Java, and there's probably a compilation error. We'll fix it if there is one, and so then we can move forward. So this is basically running the code. Looks like there is no compilation error. Okay, fine. So let's go back here and run that here. You can see that's kind of running and waiting. 5 seconds later, it's going to have to finish it, and it did, right? So enter and exit. That was not too hard, isn't it? But I want to, just for our purpose, take this. I'm going to sort it, and take a look at what it provides for us so we can kind of visualize this a little bit easily. So because I sorted it, it's going to give me that based on the index that we're going to see, so we can quickly see this. So when I look at the output, what do you notice, if you don't mind? You notice 0 was executed by thread 0, 1 by thread 1, 2 by thread 2. This made life easier, right? The index number and the thread numbers are coincidentally the same. So what do you notice here? What did you notice? The task says, I'm going to perform an I/O. And what did the thread say? No problem. I'm here, waiting for you. When you're done with it, we'll keep moving. So this is like the irresponsible parent sleeping when the child is sleeping, right? The thread is underutilized. Am I making sense? So that's basically what we saw. There's a correlation between the thread we are using and the before and after. They're exactly the same. Let's go back to this code. And I want you to see this code right here. I'm not touching any of this code. What I'm doing is, I'm just coming to this one line, and I am commenting that one line out, and I'm saying thread dot start virtual thread. And I'm removing the start from here. There are multiple ways to do this. I'm just giving you one example of it. So notice what's the change I made. I didn't touch the code that is doing the actual work. I'm just going here to the location where I'm creating the thread. It could have been execute a service. So where I'm creating the execute a service, I can tell it, don't use a normal thread, use a virtual thread. Am I making sense? But you're not changing the actual code. You're just turning a switch here. What concept in programming comes to your mind when you can have every code here, but you can alter something here and have an impact in all the other places? What idea comes to mind? AOP, aspect-oriented programming, right? What if threads are aspects? You can modify your aspect here, and the behavior changes over there without you having to modify the code. So what if we think about a virtual thread as an aspect? So we just stood here and said, hey, that code is there. I'm going to just fiddle with the threading over here. Whether you're using threads, you wouldn't, or you can use execute a service to do it, right? So, but what's the benefit of this? The benefit of this is, when I run the code this time, let's see what's going to happen. So I run the code again this time, and when I do, let's take a look at the output. What did you notice? This is entering with 1, and it says, entering with 1, but after with 3. Did you see this? So the after should come after enter, but let's just take a look at it. 0 and 0, because I sorted it. So 1 and 3, what did you notice? For the 1, what do you notice here? You came in on 2 and it finished with 2. What about for the 2? For the 2, for the 2, it came in with 3 and finished with worker 4. I'm looking at the very last digit here. And look at the next one. It came in with 4 and finished with 5. And what about for this one? It came in with 5 and finished with 1. So what are you noticing here? Mounting and unmounting, isn't it? Because when you came in before the I/O, it said, worker 1 is doing the job. Oh, I'm making an I/O. Oh, I unmounted. The carrier thread says, see you later. And you're like, oh, my I/O is done. All right, I'm going to give you worker 3 to finish your job. That's the mounting and unmounting you're noticing. Because you're mounting and unmounting, you can now have a lot of tasks running. And you need very few threads than you would otherwise, isn't it? So to summarize this, I want you to think about what the consequence of this is. Going back to this, let's jot it down. So remember that story, right? So we talked about the past, what Java 8 did and what Java 8 did with Complete Future. With Java 21, the structure of imperative style asynchronous code is the same as the structure of imperative style synchronous code, thanks to whom should we thank? Virtual threads. Hope that was useful. Thank you.